Okay, so suppose we are in this rare situation where we can approximate our operator A uniformly by a sequence AN that can be treated numerically. So we have uniform convergence AN to A, and we want to solve AX equals B by means of solving AN xn equals Bn. Okay, now we have uniform convergence here, and we have convergence in the space Y here. Do these solutions xn exist, and do they converge to X? These are our two questions, or our two hopes. Okay, so let's rewrite our two equations for the solutions that we're actually interested in. Well, the solution of the original equation is x equals A inverse B, and we can write that because we are assuming the existence of the inverse. But of course we cannot compute it that way, because computation of the inverse operator is notoriously difficult and expensive. Okay, but because we are expecting unique solvability also for these equations and for arbitrary right-hand sides Bn, as long as they converge to B, we will also expect invertibility of these operators An. Well, let's say at least for all sufficiently large n, let's say n greater than or equal to some n0. But then we can write also their solutions as xn is An inverse applied to Bn. And we can ask, what is it that we need for our convergence here? Well, because we guarantee this convergence of Bn to B, the only thing that's missing is convergence of the inverses of An to the inverses of the inverse of A, and preferably also that in the uniform sense. So that convergence here would seal the deal. Okay, so in a nutshell, given an invertible operator A and the uniform approximation of A, follows the invertibility of the approximants for sufficiently large n, and the uniform convergence of the inverses that we mentioned above. Question mark. So this would guarantee existence of unique solutions for sufficiently large n and convergence of these solutions to the solution that we are actually interested in. So in other words, this is what we need for applicability. So for our goal of understanding this mechanism here, let's guide ourselves by the following two questions. First question: if An is sufficiently close to A, will the property of invertibility jump over from A to An? And second, does uniform convergence of the inverses follow from uniform convergence of the operators? Which is of course what we're asking here. And the first one of these guiding questions brings us directly to lemma 1. And maybe just unofficially we could call it invertibility is infectious. But here's the correct statement. Let A be an invertible bounded linear operator from x to y. Then there exists a positive radius epsilon depending on A, such that every operator B in the epsilon neighborhood of A is also invertible. So if this is the set of all invertible operators from x to y, then around every element of that set, so around every invertible operator A, you can draw a circle, and the radius of that circle depends on A. That is still entirely inside the set of all invertible operators. Okay, so the radius is what we call epsilon in this theorem, and we will even see how epsilon is computed if you know A. Well, maybe if you don't want to wait until the end of this proof, here's a little spoiler, but let's try to see ourselves. Okay, for mathematicians that means proof. We start with a little baby case that is fairly simple but helpful for the general case, and that's case A, where spaces x and y are the same and the operator A is just the identity operator. Now obviously that is invertible. We will see how large a radius around the identity can be so that it contains only invertible operators. And maybe we can even draw some inspiration from the real line here, because I mean in the end real numbers are just operators. They are one by one matrices. Only one of them is not invertible, that is the 0, and here's the identity, which is called 1 in the real axis. So how large a circle can you draw around the unit here, around 1, without it containing any non-invertible elements? Well, this one would be fine, but in fact, well, you could go up until right before the 0 element. So the radius could be 1, because we're saying less than epsilon here. So let's say we're talking about this point x here, which has distance, let's say a little q, less than 1 from the unit. So x is 1 minus q, and we know x is invertible, right? So we can, instead of writing x to the power minus 1, we could write 1 over x, which is now 1 over 1 minus q, and I hope you remember the formula for this. You should remember the geometric series, so you just take powers of q, and you're starting from the 0th power and continue without end. And this is guaranteed to converge if the modulus of your q is less than 1. Okay, so this was just a little source of inspiration here. But let's see what we can do with that in the operator world. So instead of our real number x, take an operator b and let it be the identity minus, well, maybe operator q instead of little real number q. And let's try to talk about inverses. Okay, and let's be optimistic, so maybe the following just works. Okay, so first let's check whether this series actually converges, and then we will see whether or not it's indeed the inverse of I minus q. So convergence, abbreviate the partial sum, so the series truncated at n by Sn for every natural number n. Okay, and then showing convergence of that series just means showing convergence of that sequence here. And it's kind of difficult to show whether that sequence converges, because for convergence you need the limit, and then you could write something like this. Okay, and then along the lines try to argue that this goes to 0, and there you are. Trouble is, you don't have no limit here, so you don't know what to write for S. You cannot write this expression, you cannot write this inverse, you just don't know what to do. Okay, and this is where the sheer power of completeness kicks in, because now you only have to argue via Cauchy sequences, so you don't need that limit here. So instead you just check how large the difference of two such operators is. But by their definition, and assuming m is less than or equal to n, you just get this. which you can bound like that by triangle inequality. But this you can further bound by that, where here you're just getting this exponent out, and you can do this by the following little inequality. If you didn't convince yourself of that little inequality, so the norm of a product less than or equal to the product of the norms, then try to convince yourself now, and if you cannot, then ask me in the next question meeting. Okay, but now we could relabel this norm of the operator q as the real number little q, which would give us this. But then we are down to the geometric series, so we can bring this home very easily. Maybe like this, which is just the geometric series in disguise, and therefore has the following formula. Okay, but now it's clear that this goes to 0 as n goes to infinity if our number little q has modulus less than 1. But little q is just the norm of the operator q, so now we know what we have to put here. Okay, so it follows that the sequence Sn is a Cauchy sequence in Lxy, which is just Lxx in our case, because we are assuming x equals y for the moment. Okay, and at this point we will argue with completeness. So because x is complete, of course we have to assume that from the very beginning, it follows that also Lxx is complete. Well, in fact, you need that x to be complete, but it's just the same for this argument. We can say that this Cauchy sequence is convergent and has a limit in Lxx, which we will, as usual, just abbreviate by Lx. And the convergence is in the sense of the operator norm, so we are now denoting this by a double arrow. It's uniform convergence. Okay, so let's tick this one off. Convergence is clear. Now it remains to show that this series, which exists, which converges, indeed gives you the inverse of I minus q. Okay, to see this, let's just multiply the two and see if we get identity. Then rewrite S as what we have. It's the limit of the sequence Sn. And then, because the limit exists, let's rearrange brackets here and plug in what Sn is. Okay, now let's fiddle around a little bit in that black bracket, where q to the power k times I is what we see here, and q to the power k times q is what we see here. And now maybe relabel k plus 1 as L, giving you this. Okay, and then if you look, this first sum adds up the powers of q from exponent 0 to n, where the second sum adds up the powers of q for exponents from 1 to n plus 1. So most of these cancel, only the ones at the boundary remain. But okay, that one is defined as the identity operator, and that one tends to 0 since its norm can again be bounded by this rule. Okay, and that goes to 0 as n goes to infinity. So indeed that limit turns out to be the identity. Essentially the same computation also works when you just exchange factors here. Okay, and that finishes the proof of our part A. So again, let's celebrate the statement of part A. So indeed, what you call geometric series for numbers again works for operators, now only that now you call it the Neumann series. Maybe note that that Neumann guy here is not the famous John von Neumann, but another mathematician called Carl Gottfried Neumann, who lived 100 years earlier. Okay, let's have a quick look what we've done. So we are still in the middle of proving our lemma 1. Invertibility is infectious. So if you have an invertible operator and you go away only a little bit, then you're still invertible. Now we also quantified how far can you go away from the identity. Well, it's written down here. So in this case, little epsilon turns out to be 1. Okay, let's come to the general statement. So let's make this part B in our proof. So the spaces x and y need not be the same anymore, and A could be any invertible operator between them. So again, look at another operator B, which is just A minus some Q with norm of Q less than epsilon. That is still to be determined here, and find out whether or not that B is invertible. And now the trick is to reduce that case to the previous case, to this baby case A, by getting A out of the game here and just writing this as A times, and then see what remains. Well, in the bracket we have identity minus A inverse times Q. Can you see how this product turns out to be just what is written here? Okay, excellent. So let's check spaces quickly here. So A goes from x to y, right? So B also goes from x to y. So our Q must go from x to y. Now here A goes from x to y. And the identity in that bracket must be from x to x. Q is, as we know, from x to y, and the inverse takes that from y to x. So indeed, the situation inside that bracket is just like in case A. So in particular, we know that when the norm of this thing here is less than 1, then this bracket will be invertible by Neumann series, or statement A. But of course, A itself is also invertible by assumption. And then the product of two invertible operators is always an invertible operator. Just try to convince yourself that this is true, and if you cannot, then ask us in the problem session. Okay, so at the end you see that indeed this whole thing is an invertible operator, showing that B is invertible. So let's quantify that. So B is invertible if, well, the norm of A inverse Q, which we saw here, is less than 1. Now, because this norm is less than or equal to norm of A inverse times norm of Q, one could argue that if this is less than 1, then that norm will also be less than 1. Okay, and how can you guarantee the latter? Well, that is easy. We just make the norm of your Q, by which you are perturbing your original operator A, smaller than 1 over the norm of the inverse of A. Okay, and that is our mysterious epsilon from the theorem. Job done. Okay, so let's celebrate our achievements a little bit. So we have proven this lemma 1. So now we know that invertibility is infectious. If you're invertible, then everything around you, at least in a small neighborhood, and we can quantify that, is also invertible. By the way, sets with that property are called open sets, and one can show that a set in a metric space is open if and only if the complement, that is the whole metric space minus that set, is closed. But that is just on the side. Okay, but that clearly positively answers our guiding question number 1. So if you're sufficiently close to A, then invertibility, yes, it jumps over from A to AN. Excellent.